In this video, I want to talk about bases other than base 10. And I want to be very upfront. This is information that is often, that students sometimes struggle with. This is some of the most abstract stuff we deal with in this course. A lot of what we deal with this course is items that you've had at least in some version before in your education. Now, we often look at them a different way. So for example, you have all at some point been taught how to multiply. Later in chapter 3, we'll learn about techniques for multiplication that are not the way you probably learned. The one thing that we don't really teach in schools is bases other than base 10. Now, I mentioned in a previous video that the Mayans used something very much like base 20 and the Babylonians used base 60. The base that we use is 10, and that means that we have 10 digits and we are based on powers of 10. So we have 10 digits to write every number from 0 to 9, and then we have 10 digits to write every possible number from 10 to 99, and then from 100 to 999, and from 1,000, and so on. And so when we do a number in expanded form in our base 10 system, if we'll do a short number like 3,417, that is 3 times 10 to the third, just thousands, plus 4 times 10 squared, which is hundreds, plus, let me erase that, plus 1 times 10 to the first, which is 10, plus 7 times 10 to the 0, which is 1. And so one way to help you, I think, in other bases is to think about what this means. What this really means is that I have here 3 groups of 1,000. I have 4 groups of 100. 4 groups of 100. I have 1 group of 10. And I have 7 groups of 1. And then I add each of those groups together. 3,000 plus 400 plus 10 plus 7, and I get 3,417. We do the same thing with other bases, but the other bases aren't built on powers of 10. They're built on powers of some other number. Base 2 is based on powers of 2. So we have 2 to the 0, 2 to the first, 2 squared, 2 cubed, 2 to the fourth, 2 to the fifth, 2 to the sixth. Base 7 is based on powers of 7. So we have 7 to the 0, 7 to the first, 7 squared, 7 cubed, 7 to the fourth, 7 to the fifth, and so on. One system that is commonly at times used in elementary math is the base 5 system. And your book uses the phrase quinary or quinary for it, and your book is the one place that I have ever seen this used. So take that for what you will. There are base 5 blocks out there, allegedly. I think base 5 blocks tend to be a relic of the 70s. Back in the late 60s and early 70s, other bases were widely taught in elementary school. It did not go well, primarily because most teachers weren't knowledgeable enough to teach it well. And at about the same time, in addition to base 10 blocks, blocks that in other bases started to show up. When I taught math methods, I tried to find some of those other blocks, and I never could. So I don't think they're widely available anymore, but they still show up sometimes in textbooks like this one. So I don't know that this is super helpful in understanding what base 5 is. I think it might be easier here if we count in base 5, and using the blocks here is helpful. Or using the symbols here are helpful. We aren't going to worry about 0. I mean, 0 is in every system. One thing you need to know is that when you work in a base other than 10, you have to put the name of the base as a subscript after it. So we read this as 1 base 5. The other thing you need to know is that this is not a 10, this is not an 11, this is not a 12, this is not a 20. Those are words that have meaning in base 10. They don't have meaning in base 5. So how we count in base 5 is like this. 1, 5, 2, 5, or you could say 1 base 5, 2 base 5, 3 base 5, 4 base 5, and then 1, 0 base 5, 1, 1 base 5. And I'm not going to say 5 each time. You just have to write 5 when you do it. 1, 1, 1, 2, 1, 3, 1, 4, 2, 0, 2, 1, 2, 2, 2, 3, 2, 4. One important thing to notice is that there is no digit 5 in base 5, just like there's no digit 10 in base 10. Our equivalent of 5 is 1, 0. 1, 1 is 6, 1, 2 is 7, 1, 3 is 8, 1, 4 is 9, 2, 0 is 10. Why is that? Think about our system here. In base 5, we have groups of 1 still, but here our 1s are 5 to the 0 rather than 10 to the 0. And then we have groups of 5 rather than groups of 10. So the number 1, 0 in base 5 is 1 group of 5 and 0 groups of 1. So it is 5. When we write it without a subscript, we know we're talking about a base 10 number. So the number 2, 3 in base 5 is going to be 2 groups of 5, and these aren't fraction bars, they're just underlines. 2 groups of 5 and 3 groups of 1. 2 groups of 5, that would be 2 times 5, that would be 10, plus 3 groups of 1, 3 times 1 is 3, of course. So 2, 3 in base 5 is 13 in base 10. In my experience, in the praxis exam, the licensure exam for elementary teachers, which I took a few years ago, I've taken it more than once. I took it when I first had to take it as a graduate, when I moved to teach in Nevada. And when I was adding some licensure, a couple of years ago, I had to retake it because my original scores had expired. And so I took this exam probably in like 2018. I think 2018 or 2019, I think 2018. And one of the things I noticed still that I had to do when I took it originally, and I still had to do, is I had to work with other bases than base 10. And so this information in this particular section of your textbook is going to be important for you. It's not that you're probably going to teach other bases to your students. The idea is by understanding how bases work, other bases, by understanding base 5 or base 8 or base 2 or base 16, you understand base 10 better. And that was the whole point of teaching other bases to students when that was tried in the late 60s and early 70s. And it's a valid point. Using another base helps us understand base 10 better. Just like learning a foreign language helps us understand, usually helps us understand our native language a little better. I've had students tell me that they didn't really understand English grammar until they studied, Spanish or French or Mandarin or something else. So when we convert from another base to base 10, you should do something like this. What this is telling me is how many different groups. This is 4 groups of 1, 4 groups of 5, 2 groups of 25, 1 group of 5 cubed, which is 125, and 1 group of 5 to the 4th, which is 625. So you might get a chart like this. And then, this is in reverse order, I do that multiplication. So this is 1 times 5 to the 4th, plus 1 times 5 cubed, plus 2 times 5 squared, plus 4 times 5 to the 1st, plus 4 times 5 to the 0, which is 4 times 1. So that equals 1 times 625 plus 1 times 125 plus 2 times 25 plus 4 times 5 plus 4 times 1, which works out when we add those all together to 824. The number 11244, base 5, is 824 in base 10. In my experience, the only way you get better at making these conversions is by doing them, by doing lots of practice. And I strongly encourage you to do that in this section. Do beyond the homework assignment. Go through that assessment A and do practice problems for converting bases, because it's something that you as potential elementary teachers are expected to be able to know and to be able to work with. So I'm going to try to move over to my tablet and record on that and see if that works. So we're going to pause here and see. All right, so I'm going to hope that this screen is showing up. Otherwise, I'll have a lot of editing to do. So let's do another couple with working with base 5 first. And we're going to do more than just base 5 because it's something you need to know. So let's say I had the number 204,857 base 5. So what I have to ask what I'm realizing, this is different groups. So it's probably best to work from the right to the left here, especially at first. But maybe I'll try it like they did on the PowerPoint, and I will make a little table. And I have, what, 6 digits here? So 1, 2, 3, 4, 5, 6. So I'm gonna do it like this: 204,857, and then I'm gonna put my powers of 5 underneath it. So I have 5 to the 0, which is 1. I have 5 to the first, which is 5. I have 5 squared, which is 25. I have 5 cubed, which is 125. I have 5 to the fourth, which is 625. And I have 5 to the fifth, which is 625 times 5, which is 3,125. So I think the first step you should make, and it doesn't matter how you do it, is to draw something to let you know what you're looking at. And what this is these are groups. These are groups of different values. I have 2 groups of 3,125. I have 0 groups of 625. I have 4 groups of 125. I have 8 groups of 25. I have 5 groups of 5. I have 7 groups of 1. This is the same idea as expanded form in base 10. Base 10 is just simpler for us because we're used to it. We say, oh, I have groups of 1,000 or groups of 100 or groups of 10 or groups of 1. Here, instead of powers of 10, we're dealing with powers of 5 because we're in base 5. And I made 2 mistakes. Can you tell my mistakes? There are no digits 8, 5, or 7 in base 5. So let's do this instead. Okay, that's a very common mistake. I'm sad that I made it, but people do make mistakes in math. There we go. Here, 204,134 base 5. So again, when you first saw that, hopefully alarm bells went off, or at least you thought, wait, I don't get it. Hopefully now you do. The digits of another base will never equal. You'll never get a digit that's 5 or above in base 5. Just like we don't have one digit that means 10 in our base 10 system. We use 2 digits for base 10, or for the number 10. And in base 5, we use 2 digits for the number 5. So, now that that embarrassing part is cleared up, let's write this in expanded form. 2 times 5 to the 5th plus 0 times 5 to the 4th. I like including the 0 here. You don't technically have to, but I find that if I don't, and I find sometimes that if students don't, they forget about this 5 to the 4th, and they write 5 to the 4th for the next one. Then I have 4 groups of 5 cubed. I have 1 group of 5 squared. I have 3 groups of 5 to the 1st, or just 5. And I have 4 groups of 5 to the 0, or 1. So 2 times 5 squared, that is 2 times 3,125. I'll just put a 0 here now because I have my other stuff. 5 cubed is 125, so it's going to be 4 times 125. 1 times 25 plus 3 times 5 plus 4 times 1. And this is a mistake that people sometimes make. They think 5 to the 0 is 0, or they think 5 to the 0 is 5. Any number to the 0 other than 0 to the 0 equals 1. So 5 to the 0 will always be 1. So 2 times 3,125, that's going to be 6,250, plus 4 times 125 is 500, plus 1 times 25 is 25, plus 3 times 5 is 15, plus 4 times 1 is 4. So when I add these together, I think I can add this in my head. This is going to be, this part will be 6,750, 6,775, 6,794. So 204,134 in base 5 is equivalent to 6,794 in our base 10. Let's do one more with base 5. We'll make it a little bit shorter. Let's do 4444 base 5. And again, I want some sort of chart or something just to help me keep track of things. So I have 5 to the 0, which is 1, 5 to the 1st, which is 5, 5 squared, which is 25, 5 cubed, which is 125. If I were doing this on a test and was stressed out, definitely use my calculator to double check on what like 5 cubed was. You're not, that's something you probably know if you've done lots of exponents, but if you don't know it, by all means, use your calculator to check, especially in a stressful situation like a test might be for some people. So 5 cubed is 125, like I said. So in expanded form, I have 4 times 125 plus 4 times 25 plus 4 times 5 plus 4 times 1. So I'm going to have 500 plus 100 plus 20 plus 4. So that's going to be 624. 4444 base 5 is 624 in our base 10. So I hope those examples helped. Again, the best way I can describe this is to think of this as groups. And we haven't talked about multiplication yet in the course, but remember from elementary school, the multiplication sign really means groups of. 4 groups of 125, 4 groups of 25, 4 groups of 5, 4 groups of 1. Another base that's very common is base 2, and base 2 is commonly known as binary. Base 2 is the base that your calculator uses. It's the base that every electronic gadget uses because base 2 has just 2 digits, 0 and 1. And that is how computers and calculators and other electronics work. There's either electricity flowing or not. It's 0 or 1. It is on or off. And that's what binary is. And so when your computer adds numbers together or subtracts or does anything else, it does it using base 2, using binary. Now, at one point, binary was taught because it was thought wrongly. That's how people would communicate with computers. Today, that's not true. Using machine language, the sort of the closest you can get, is still occasionally done, but it's by a very, very, very small group of people. Even computer programmers aren't likely to use base 2. They are, though, interestingly, likely to use bases beyond base 2. They are likely to use base 8, and they're even more likely to use base 16. That also includes people doing electronic graphics. We do the same process in converting a number to base 10 from base 2. We have 2 to the 0, which is 1, 2 to the first, which is 2, 2 squared, which is 4, 2 cubed, which is 8, 2 to the fourth is 16. So we have 1, 0, 1, 1, 1, base 2. And then that means we have one group of 16, 0 groups of 8, one group of 4, one group of 2, one group of 1. We add those together and we get 23. We'll do another example. So remember that because we're in base 2, the only digits we can use are 0 and 1. So we're going to look at a really big number here. And there are different rules for putting commas sometimes in numbers for other bases. I like putting them in there, even though I don't think you're technically supposed to, just because it helps me group them so I can read them a little bit better. So, and again, this is base 2. I should write that in there. Base 2. So what I'm going to do is make my chart. And I see I have 3, 6, I have 12 digits. So, there we go. And I'll put my 2's up here, I guess. So I have 2 to the 0, which is 1. I have 2 to the first, which is 2. 2 squared is 4. 2 cubed is 8. 2 to the fourth is 16. 2 to the fifth is 32. 2 to the sixth is 64. 2 to the seventh is 128. You notice with powers of 2, it literally just doubles each time. 2 to the eighth is 256. 2 to the ninth is 512. 2 to the 10th is 1024. And 2 to the 11th is 2048. Again, you wouldn't have to make a chart like this. Sometimes a person just sort of jots them down above the number or below it itself. I just find, especially when you're first doing this step by step as you can is beneficial for most people. And so what this tells me is I have one group of 2048, 0 of 1024, 1 of 512, 0 of 256, 1 of 128, 1 of 64, 1 of 32, 0 of 16, 0 of 8, 1 of 4, 0 of 2, and 0 of 1. And so because I don't really have any multiplication to do here, I'm just going to add these together. And I'll add them by hand, I think. So I'm going to have 2048 plus 512 plus 128. 64 and 32 is 96. Excuse me, plus 4. So I added a little along the way. In fact, I'll add these two too to make it 96 plus 4 is 100. So 64 plus 32 plus 4 is 100. That will make my addition a little bit simpler for me. So 8 plus 2 is 10, plus 8 is 18, 1 plus 4 is 5, plus 3 is 8, 7, 2. In base 10, that number is 2,788. So when I type that number in my calculator doesn't see 2,708. When it goes to work with it, it sees instead this sequence, this sequence of digits here. Same thing for your calculator. So that's an example of converting from base 2 to base 10. This same approach is used for every other base. If we were doing base 8, we could have digits from 0 to 7, and we would have our place values would be 8 to the 0, 8 to the 1st, 8 squared, 8 cubed, 8 to the 4th, 8 to the 5th, and so on. I don't know if your textbook talks about bases like base 16, which is hexadecimal. I want to talk about that just a bit. So bases bigger than 10. In bases bigger than 10, we use letters rather than numbers to represent those digits. So in base 16, whoops, that's not going to help me. In base 16, our digits are these: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or not 10. We always want a single symbol. So just like the ancient Greeks used letters for numbers, we use letters for numbers when we're dealing with bases bigger than base 10. Then we have 10, 11, 12, 13, 14, 15, and we stop because the number 16 in base 16 would be 1, 0. Just like the number 8 in base 8 would be 1, 0. The number 5 in base 5 is 1, 0. The number 2 in base 2 is 1, 0. So if I were kept counting, I would have then 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. And again, technically, I would want to put a 16 after each of those. You don't have to do that if you're doing a whole long list of them, though. Just doing it once is going to be enough. So, but the digits for base 16 then are the R digits 0 through 10, and then we use letters to represent the values, our digits for 0 through 9, and then we use letters to represent our values from 10 through 15. Remember, it's always one less than the base. So if I have a number in base 16, like the number C4, this means I have, so A is 10, B is 11, C is 12. I have 12 groups of 16 to the first plus 4 groups of 16 to the 0. So I have 12 times 16, which I'm not going to do in my head, sorry, which is 192 plus 4. C4 in base 16 is the number 196 in base 10. Computers use base 16 a lot because it lets them represent larger numbers with fewer digits, which saves memory. And so sometimes if a person is working with graphics, you'll notice that there are different values for reds, greens, and blues on your computer screen, and those values, you'll often see these letters included with those values. That's because those values are in base 16. You also need to be able to convert from base 10 to other bases. That's trickier in my opinion. Whereas converting to base 10 involves multiplication, converting from base 10 involves division. So this is one way that your book suggests doing it. So we're converting 27 to base 2. So what we want to do is first on the left-hand side, we want to put our powers of 2, starting with 2 to the 0. So we have 1, 2, 4, 8, 16, and we go until we get to the number that is just below the number we're trying to convert. So 32 would be too big. 32 doesn't go into 27 at all, obviously. 16 goes into 27 once. We write that answer on the right-hand side, like so. So, and then we subtract, just like we would in typical division. So we have 11. Then our next power of 2 is 8. 8 goes into 11 once. We subtract. We have 3. 4 doesn't go into 3 at all, so we put a 0. We still have 3. 2 goes into 3 once. We subtract. 1 goes into 1 once. And we, at the end, have to have a 0 as a remainder or something went wrong. So 27 is 11011 in base 2. We could also do it this approach where we divide by 2's repeatedly. So 2 times 13 is 26. We have 1 left over. And then 2 times 6 is 12. We have 1 left over. 2 doesn't go into 3 at all. So we end up with a 1, and 2 goes into that once. I don't like that approach, but if that works for you, use it. I've put up another, there are other optional videos, supplementary videos they're called, that deal with this. The title of them probably says not covered because I put them up for my Math for Liberal Arts class. And this is this is 2 sections in the chapters for Math for Liberal Arts, at least at Iowa Lakes. And we skip those chapters because most of my students in that class are not going to be elementary ed majors or math majors. And those are the majors who need this information. For everyone else, it ends up taking a lot of time for not a lot of benefit. So look at those videos too, because those will give you other ways of doing it that might make more sense to you. I'll do an example of converting from base 10 to another base in a few minutes here. But I want to first finish up the PowerPoint by talking about base 12, or the duodecimal system, not to be confused with the Dewey Decimal Library System. In this base, we also use letters to represent numbers bigger than 9. Your textbook uses 10 to represent, or uses T to represent 10 and E to represent 11. I wish they used A and B instead, but your textbook I don't think goes through base 16, so that's fine. So if you see this in your book, and I don't think I assigned anything from base 12, if you see T, that means that it's a group of 10. If you see E, capital E, that means it's a group of 11. So if we have the number E2T, base 12, and we want to convert that to base 10, this is what we do. It's the same approach that we've done before. We have E groups, that is 11 groups of 12 squared, plus 2 groups of 12 to the first, plus T, which is 10 groups of 1, or 12 to the 0. So 12 squared is 144. When we multiply this out, we end up with 1,618. And then we're asked to go in reverse and convert 1,277 to base 12. And here's their approach for doing that. I'm going to show you my approach for doing it, which is really similar to theirs. And I'm not saying mine is better. It just works for me. But the PowerPoint is also up on Canvas, so you can either pause the video if you want to really inspect how they did it, or you can just look at the PowerPoint. So what I like to do here is start by listing my powers of 12. And so I know that 12 squared is 144. I want to see what 12 cubed is. And so let's pull the calculator up. 12, it's not being very responsive. I have too many windows open right now. 12 cubed is 1,728. Notice that 1,728 is bigger than this number, right, by quite a bit. That means we aren't going to have any groups of 12 cubed. It's too big. So this means in this number, we're going to have groups of 12 squared, we're going to have groups of 12 to the first, and we're going to have groups of 12 to the 0. Which means we're going to have groups of 144, we're going to have groups of 12, and we're going to have groups of 1. We can have up to 11 of any of these groups. We'll remember if we're working with 11, we'll write an E as our answer in base 12, and if we're working with 10, we'll write a T as our answer in base 12. So we always start then with the biggest group and we just divide. Now, this is a hard division problem to do by hand. I'm going to use the calculator and sort of show you how to work this with a calculator. So 1,000, oh, you can't see my calculator because I'm sharing the wrong screen. Sorry. Let me fix that. Okay, now you can see my calculator. Sorry about that. So I want to divide 1,277 by 144. Here's how I'm going to do this. I'm going to kind of cheat and do it using the calculator to help me. So 144 goes in there 8 times. And now I'm going to use the calculator to tell me what that equals. 144 times 8 is 1,152. Now I can subtract, and I get 125. And I know that now I don't try to go here. Now I check my next one down. And now I do this division. 12 into 125. So 12 goes into 12 once. It doesn't go into 5 at all. There's a remainder of 5. So I have 10, which I'm going to write as a T for my answer because I'm in base 12. And then finally, how many times does 1 go into 5? And obviously it goes in there 5 times. So my answer is going to be, I have 8 groups of 144, 10 groups of 12, and 5 groups of 1 in base 12. 8T5. So this is the approach that works for me. Again, the thing that you need to remember is that what you divide by changes each time. So you do a division, and then there will likely be a remainder. If there's not a remainder, then your other answers would be 0. Your other places would be 0. So you'd have 8, 0, 0. If there wasn't any remainder here, that means my next choice is going to be a 0, and so is my next choice, and until I get to whatever 12 to the 0 is. So, excuse me. I know working with bases can be complicated. That's why I encourage you to look at those other videos, as well as to do some practice problems in your textbook. I'm going to go back and finish up the PowerPoint. There's a couple of slides left. So here we have a problem-solving type of question. Rob used base 12 to write the following. G, 3, 6, 12 equals 1,050 in base 10. What is the value of G? We can find this. This looks complicated, but if we stop and think about it, it's not too bad. We know this is in base 12. So we know that we have groups of 1, groups of 12, and groups of 144. So we know that we have 3 groups of 12, that's 36. And we have 6 groups of 1, that's 6. 36 plus 6 is 42. 1,050 minus 42 is 1,080. And then we can use a calculator to see, does 144 go into 1,080 evenly? And it does not. It's something wrong here. 1,050. Oh, I didn't subtract right. It's been a long day. Yeah. So don't ignore what I just said. But again, hopefully you saw that. Like, oh my goodness, what is he doing now? Okay. Again, we make mistakes in math. The idea is, do we have a reasonable answer? We always check for reasonableness. So let's again work through this a little bit more. So we have 6 groups of 1, that's 6. And we have 3 groups of 12. So that's going to be 3 times 12, that's 36. 36 plus 6 is 42. 1,050 minus 42, let's subtract correctly here, is going to be 1,008. And so what I want to know is, this is going to be groups of 144. Will 144 go into 1,008 evenly? So it's the same thing I was doing, I just made a boo-boo with subtraction. And that is often the case. You're doing something a little more complicated in math, and what happens is that your mistake is a minor mistake, but it's still a mistake. So 1,008 divided by 144 should be a natural number. And blessedly it is, it's 7. So we know here that G must equal 7. So this number in base 12 is 736 base 12. And we could check that, and we probably should. So 7 times 144 is 1,008. 3 times 12 is 36. And 6 times 1 is 6. So we have 8 plus 6 is 14, plus 6 is 20. Carry the 2, 5, 0, 1, 1,050. So it's just a matter of stopping and thinking and then making sure your arithmetic is correct. So I know this was a super long video. It's ironic because my goal for videos is like maybe 15 minutes. I know it's supposed to be 10 or under, and this is 3 times my goal. So I don't blame you if you didn't listen to this. If you're not listening to this right now, I do not blame you. But I hope if you did listen to it, it will help because, again, this is information that you need beyond just this section, just this chapter of the textbook. This is information that will show up, most likely, on your licensure exam for elementary education. It may even show up in the PLT for elementary, for K-6. I'm not sure if it shows up on that or not. I haven't taken that for many years. But I know it shows up for, it could show up for the math parts of the LED exam.